Hi, I forgot to record my lecture during my class, so record forget to record it the lecture. So I guess I have to record it again. So okay, so today I'm gonna talk about simple sample designs. So I will cover mostly about simple random sampling and then move on to memory sampling. So I already explain what simple random sampling is in terms of the definition. So we basically we have a capital N combination, small n possible samples. So this is fixed, right? We determine. So we so determined, and then n is known. And so given capital N, if we choose particular small n, then we know how many possible samples, and then we can basically assign equal probability. That's it. And then we on the simple sampling, the first inclusion probability is this, right? And second inclusion probability are these. So we covered this already. And the lemma, so we use indicator function, and this is random variable, right? So if you repeat your sampling, you can particular unit can be selected or non-selected. But on the simple the sampling, they are all equal, right? They are all homogeneous. So then we don't have a real dependency on I. I mean the index I or J. So we just have this variance and covariance, and the covariance is negative, which kind of makes sense because we know if you select one element, then and then n is fixed, right? So I equal to n, and this n is fixed. Then if I sum of the I is equal to one, then the others will is has more chance of having zero than one, right? So that is basically the reason why we have negative negative covariance. And in fact, we showed this already, but so basically we can start from I one, and then if I have a expectation, and this is all equal, then pi I is basically, so pi I, this is pi I, it's all equal, that this means that we have n over n. And then variance, same thing, right? So I zero variance, and variance of variance n, which is zero, because this is fixed. Then we have something like this variance. So we call this f. Then we have basically n. Okay. Basically, we have this one is equal to variance of sorry, summation of variance of I plus I not equal to J covariance Ij. Okay. Make sure I recording. Okay, I'm recording now. So that is zero. So then this one is n times f times 1 minus f. These are all equal, right? This is covariance, and then we have n times n minus 1 of them. Covariance is zero. So covariance is indeed so that's basically what it is here. Or you can just use the definition, right? I mean, another way is you just use the definition of the first order inclusion property and say this is pi ij minus pi ij, and then this one is n minus 1 divided by n minus 1. That's it, n over n squared. So if you use that and simplify, you'll get this. Okay, so the first theorem is the Hurwitz-Thompson estimator on the simple and the sampling of the total is so parameter is population total. So for to estimate the parameter, the Hurwitz-Thompson estimator is something like pi I, right? And then this guy is basically n over n yi. So then n times is y power. So that is what's going on here. So it is unbiased. That's already unbiased because his Hurwitz-Thompson estimator is unbiased. And then second part is the variance. So we need to show this. But one thing I like to emphasize is that if you look at this, so if you look at the uh, what is this? So that this is actually, if you divide total estimator by the population size, that is basically mean, right? And here in this case, it's just a sample mean. So variance of sample mean is 1 over n, 1 minus 1 minus square. So you can see that this guy basically is a reduction in variance due to without replacement to sampling. So variance decreases due to without replacement sampling. Without replacement sampling. So in the eastern case, when n is capital N, right? If you select N1, then variance will be 0, right? So that is actually reflected here. So this part, because this concept is kind of important, that is sometimes called has finite population correction factor. So FPC, finite population correction. Now let's try to prove this result. So why we get this variance result? So we want to use a Jae-kwang formula. Jae-kwang variance formula. So that is applicable only when for fixed sample size. Sample design. Okay. So that is actually sen h variance over sen h grandi equal to minus 1 over half, and then double summation, and then delta ij. So delta ij, remember that delta ij is pi ij minus pi I ij, which is essentially covariance of ii and ij. And then yi minus yj squared. Okay, so this is the formula for sandwich grande. Okay, so now we want to use this formula on the simple random sampling, right? On the simple random sampling, what does it reduce to? So you could, in this case, this is we can use, right, the formula minus 1 minus n f of minus f in the lemma, right? In the lemma, we already have this result. So we use this result to here, and then yi minus n over n. So let's use f notation because f is sampling rate. So you can write Okay. Plus, so here the summation is over I or I over J, but I kind of separate out. I is equal to, so if, so the event that I is equal to J becomes a single summation, right? So to be rigorous, this is more like, you can write it this way. I, so, okay, your double summation is, can be written as a double summation with the indicator I not equal to J, right? Of something, Gij, Gij, plus I equal to J, Gij, right? So if you use that, then you can basically write it as something like this. Plus, this event is actually can be written as GII. Okay, so that you can use this technique, and then basically we have I equal to J. So if I equal to J, then the square term is equal to 0. See, if I equal to J, then they are equal. So so that means you don't have to worry about that. Okay. So then you have only to simplify. So that means you kind of have something like this, n minus 1, and then f, 1 minus f divided by f square, right? And then double summation. So then you can write it as uh, write as n times 1 minus f minus 1 times 1 over 2 n minus 1 double summation I square. And then you can write it. So then you can write it as n square over n minus f times, you can call this one as n square. So that actually gives the so proof. You may wonder what happened to, so your summation here now changes to summation over or ij pair, because when I equal to j, then the cross square term is 0 anyway, so does not make any difference. Okay. Now you may wonder why we have this equality. See, so this equality is not really difficult. If you use the double summation ij square, you can basically, this is a quite popular technique. Okay, so you can write it this way, and then see yi minus y bar square plus 2 times cross. Okay, so you have a summation ij. This is summation ij, and then yj minus y bar plus cross product, 2 times cross product. But the cross product term is 0. So end of the day, you get something like n times 2 times n times summation I yi minus y bar square. Okay. So you basically use you can write it and simplify, then you can get this equality. So this guy is equal to, algebraically equal to this. Okay. And now this is a third result. Same grand variance estimation. So So this variance estimator is unbiased for the population variance. I mean the variance of the sampling variance of the whole population estimator. So that means you can get this. So how to prove? So let's prove this. So we want to show. So to emphasize, this is a sample quantity, right? This is a quantity you can. So basically, this is a statistic or estimator, and then turns out that this SN square actually estimating is unbiased to population SN square, SN square. So then in SN square, you have a 1 over n summation a yi minus y bar. Oops. Okay. And then what you can do, you can maybe this is a little bit so this is a sample mean. I didn't use capital N, right? Did I use or not? I didn't. So let's just don't use it. So capital is just this one. Oops. Okay. And then n times y bar minus y bar square, right? And then 2 times cross product is actually algebraically equal to 0. So so that means this guy is actually, it can be written as no. So if you take the expectation, oops, then you have an expectation. And then the expectation here. So you can see that this is just this is not random variable. This is fixed. So this yi is just the quantity, and capital Y bar is just another quantity. So the on the simple random sampling, this guy will be expectation is actually n over n minus 1 to n I minus y bar squared. Okay, and then this guy is what? This guy is what? 1 over n, 1 minus n over capital N as n squared. So that means you have some expression, something like this. N squared minus 1 minus n minus n s1 squared. So then you basically can have some cancellation essentially because you have a something have some cancellation and then end up getting n minus 1 as n squared. Okay. So this guy could be multiplied in here inversely, then you show this. Okay, so that's basically what is going on. So now let's move on to proportion estimation. Binary. So in the case of binary y, you have a so your y, right? You can well is actually can be written as a yi square, which is yi, right? And then you can write it as n over n minus 1 y bar square. So that is actually n over n minus 1 times p, right? Minus n over n minus 1 p square. So basically Sn square is n over n minus 1 p minus p. So this one, right? Okay. So that is the formula of a proportion. And same way, you expectation of no expectation, and you don't have to. So small n square, same way you can obtain. See, this is a population version, right? This is a population version. This is a sample version. Oops, what's going on? Sample version, population version. So sample size, here's a population size and sample size. That's it. Then you get this variance formula. Okay. So one and as this is I already covered. So 1 minus f is called finite population correction term, and that could be, if I set this one equal to 1, means that we are making conservative variance estimation. If n equal to 1, then actually the formula here, you have a 1 here, and then you get something like this. So the meaning of this quantity is the sampling variance of the sample single element on the simple sampling, right? One sample element in the so that has a kind of a sampling variance interpretation. This Sn square does not have a statistical interpretation. It's just a definition, just a mathematical term. But this guy has a statistical interpretation. So also we can obtain central limit theorem when sample size goes to infinity. But remember, how can you make the sample size goes to infinity, right? In the finite population. So that means your finite population also increase. So this is actually a sequence. So the population size itself is a sequence that increases if you increase your sample size, something like that. I have a R markdown and I put it in the class, covered in class, but I will skip here. And margin of error is a kind of definition of margin of error is one of the half of the right, of confidence interval length. Okay. So smaller, right? Smaller d, that means it's more accurate. But you need to probably need more sample size. So yeah, half of the length in the confidence interval. And so because of the central limit theorem, we know that this guy can be computed by this one. So then to achieve this goal, that means we need to solve this inequality equation. So then basically this is unknown, but you notice that this is not really difficult because if you look at this carefully, you have 1 over n Sn squared minus 1 over capital N Sn squared. So this is known, right? This is unknown. But this is kind of population parameter. So this is usually unknown, but in the case of binary, this guy is roughly p times 1 minus p. So that means if you think of so this is actually this graph. So the maximum is occurred at p equal to 0.5, which is maximum at 1 over 4. So this is 1 over 4. This guy is 1 over 4. This guy is 4. Well, actually, no. This guy is 2. For capital, this is actually 1.96, right? But it's about 2. This is actually close to 0. So then 1 over 4, and this is a 4. So that we can get some cancellation and have a very nice inequality. So if t is, for example, 0.03, then means that the sample size is 0.03 to the minus you know 2, which is roughly 1,000. So that is kind of a typical sample size. Okay. Well, I have some explanation in the class, but this is pretty much clear. So you can read it. I will skip this part and just read it if you are interested. And I will move on to Bernoulli sampling. So in Bernoulli sampling, uh, the feature is that in the unequal probability sampling, right? No, sorry, non without replacement sampling. So without replacement. Create the correlation, right? The correlation between sample indicators, which complicate the problem. So the easiest one to make the algebra simple is just make a independent IID selection. So it's like a Bernoulli trial. And then N is the realized sample size. And 0 is defined to be expected sample size. But here, this is, we assume pi i's are all equal. So then we end up getting n times pi, right? So that is the expectation. So basically the sample size, the realized sample size follows the binomial distribution, right? This is independent. Some of the independent IID, Bernoulli trial, then it is binomial distribution. And so the estimator itself is very simple. And variance, if you look at the variance, see, so you can write it. So you can actually write it as a like covariance variance of ii, and then pi yi square, and this guy is pi 1 minus pi, right? So then, and by the way, pi is n0 divided by n, and so that will actually give you this kind of a formula, and and so variance is a little bit strange that your s square. So this is on the simplest example, this would be s square, right? But the s square is now changed to uh so this is kind of variance. This is a kind of expected value of y square, right? So we are not really subtracting the mean. Okay, here's some example you can think of. So suppose we are interested in estimating the proportion of students who pass a certain test in a university, and there are 600 population who took the test at the university. So among the 600, we select about 1/6 and using dice, and end up obtaining 90. So the sample size, expected sample size is what? It is expected sample size is a Bernoulli trial, so it's 600 times 1/6. So the expected sample size is 100, but the realized sample size is 90. And then among the 60 sample, 90 sample element student, 60 students were found to be passed. So y hat would be Thompson if you use this formula, you get n divided by n, 0, and summation over yi. Here yi equal to 1 if passed, right? Non-pass. So so we know that among the 90, we know we have a 60. And then n is 600, and n0 is what? Is 100. So sorry, 600. So 360 uh, people passed, and then estimator of the proportion. So then among the divided by 600 is what? 0.6, right? So that is the proportion, estimated proportion of P, passing probability. But that is a little bit strange. Why? Because we know from the sample that among the 90, we got 60 students passed. So from the sample, we know 60 out of 90 passed. So the p hat from this number is actually 2/3, right? But if I use Bernoulli, we got this number. So something's not really correct, or something's kind of weird, right? So if you look at that, that is a little bit quite weird, because in the existing case, even if all the students pass the exam, right? If all the students pass the exam, the whole becomes estimator. So if you among we have 90, right? 90. So if you have a 90 here, then we should have a 540. So 540 divided by 600 is a 0.9. So we got only 90% of proportion who passed the exam, but everybody passed. So something's not really correct, right? So that is the problem with the Bernoulli sampling. So N is the realized sample, but Hooft-Thomson estimator is actually doing some adjustment to reflect the differential discrepancy between the realized sample and observed sample size, realized sample size and observed sample size. That create a problem. So this actually is kind of a noise, right? We add noise to the sample mean and create the additional randomness. And the randomness is actually due to the randomness in the sample size. So the randomness in the sample size create a variance, additional variance. Okay, I think that's pretty much all. There's some further discussion of the comparison of variance theoretically, but that requires some Taylor expansion. And I will cover this one in later classes. We are not going to discuss Taylor expansion for now. So I think that's all for today, and see you next class.